the contents here, I'll give a short introduction to myself and MOTS, then an overview of the Thames Tideway project, a bit in terms of how the actual problem for the Deptford Church Street shaft was defined, then go into how we've planned the model, the inputs to the model. I'll then pause the presentation to give you a sort of walkthrough of the model itself and point out some key aspects to the modeling process. Then a brief discussion on the structural connections and how we modeled those, and then a bit more of an in-depth look at the results before finishing with just a few photos from on-site. So firstly, a quick introduction of myself and Mott MacDonald. As Edmund said, after graduating in 2008, I joined the Foundations and Geotechnics team at Mott MacDonald, and since then I've been involved in a wide range of projects covering many different aspects of geotechnical and underground structural engineering. A couple of notable projects that I've been involved in are shown here. The one on the left is Mushrab Station, which is the main interchange station on the Doha Metro. And on the right, I'm sure most people are familiar with the Crossrail project through the centre of London. Mott MacDonald is a global consultancy operating in multiple locations, and there's some headline facts and figures shown along the top here. We have specialists in all aspects of foundation and geotechnical engineering after many years delivering major infrastructure projects around the world, and we're constantly striving to embrace new innovations that will improve the way we work. Again, just a couple of major projects we've been involved in shown here. So I'll move on now to an overview of the Thames Tideway project. In the 1860s, London's sewer network was designed and constructed to meet the needs of about 2 million people, with a capacity for double this number. But by 1920, this capacity had been reached and it's been growing ever since. The population estimates into the future clearly indicate that a solution is required to upgrade the capacity of the network. So the solution is to install a 32-kilometre long, large diameter tunnel below the river with interception points along the route, so that during periods where the capacity of the existing network is exceeded, any overflow is diverted away from the River Thames and taken for treatment. This is a plan view of the Thames Tideway route through central London, and the project is split into 3 sections, west, central and east, and Mott MacDonald have been working as designers for the Costain Vinci Bashi joint venture on the Thames Tideway East section. The overall cost of the project will be just under £4 billion, and the East package makes up about 600 million of this. This schematic shows the route specifically of the Tideway East section, which forks at Chambers Wharf here, with tunnels totaling about 10 kilometres running down to the Greenwich and Abbey Mills pumping station, and then there's a connection through to the Beckton sewage treatment works for treatment of the overflow. This is just a timeline of the project. So planning was approved back in 2014, and construction has been ongoing since about late 2015. With program is that it will be finished in 2024 and operational. So that's just an overview of the project as a whole for those that weren't familiar with Thames Tideway. I'll now move on to the specific intervention shaft modelling that's the topic of this webinar, which is the Deptford Church Street shaft. And just for clarity, that's down here, just next door to the Greenwich pumping station, south of the Isle of Dogs. The shaft itself is located on this triangular patch of land between Deptford Church Street to the east, an overground railway line running on the south side, and St Paul's Church, which is situated to the north of the site. I'm just having to pause every time I change slides because I can see it's taking a while for it to feed through to everyone in the audience. So that's why I'm just pausing slightly. Here's a three-dimensional arrangement of the shaft elements. So below Deptford Church Street, we have the existing combined sewer, which runs down to the Thames. A new interception chamber, shown here in green, will be installed to allow the excess flow from this sewer to run through what's called a combined sewer overflow, or abbreviated to CSO, and that runs into the shaft where it drops and enters the Greenwich connection tunnel in red. The shaft itself is about 50 meters deep and with an internal diameter of about 20 meters, and the primary lining is formed of 1 meter thick diaphragm wall panels. And there's also this ventilation chamber associated with the shaft to provide ventilation to the tunnel itself. So part of our role in the project was to provide independent checking of the contractor's wall design of the shaft. So we needed to create a numerical model to determine the design forces in the primary lining, which was, as I mentioned, a 1 meter thick diaphragm wall. We also gave ourselves secondary objectives in the modelling, which were sort of considered nice to haves rather than absolute necessities, which were to try and determine structural forces in the cast in situ secondary lining, the base slab of the shaft, and the cover slab, which was at ground surface to close off the shaft. And we needed to provide results for structural checks for both serviceability and ultimate limit states. So one of the key stages in the development of any numerical model is the planning. And this is particularly important for 3D modeling, where model runtimes can become quite large, so mistakes in the model can lead to a lot of abortive work. So making an extra big effort early on in the process to properly plan models is invariably time well spent. So part of this planning should include production of sketches that define the model geometry and boundary conditions adequately. So here's some sketches that were produced, a plan and a long section through the shaft and the tunnel. That again, so you can define overall dimensions, boundary conditions, zones of where we think we might need finer or coarser meshing. And producing sketches such as this gives the modeler the opportunity to optimize the meshing by rationalizing geometry at an early stage. So remember, approximation of reality. So for example, this is a sketch that is more detailed on the actual section through the shaft itself. And you can see that there's a transition in ground stratigraphy, the green lines, at 77.5 meters between the Thanet sand and the chalk. So therefore, it was decided to simplify the model to put an excavation dig stage there as well, so that those are coincident lines. And you'll see there's various points in the model where the geometry has been rationalized to simplify down the mesh. Other things such as water levels, and geometry of structures can also be included on these sketches. And that's just a final example of a sketch that was done for setting out the tunnels relative to the shaft. And so in an ideal world, once the planning is completed, there should be a set of sketches that have sufficient detail on that they could be passed to someone else to actually set up the model. And that way you know that you've captured all the information that would be required. And it's good practice to get all these sketches agreed with whoever the designer is. If someone's going to be different, is going to be designing it rather than modeling it before we start the modeling, to ensure that the objectives and limitations of the model are fully understood by everyone involved. So I'll now run through the main inputs that went into the numerical model of the shaft. First, from a geotechnical perspective, is the stratigraphy at the site, which is typical of East London, where we have river terrace deposits, which is a coarse gravel, overlying Thanet sand over chalk. The groundwater regime is hydrostatic from about 7 meters below ground level in the short term as a characteristic line. And this characteristic groundwater pressure profile was applied to the analysis with outputs factored up accordingly for ULS design checks. This table just summarizes the material parameters used in the model. So all the materials were modeled as with Moore Coulomb parameters, all drained as well. Fairly typical parameters for the materials, but note that the in situ values of K0 that were applied in the model will be lower than the actual in situ values, but due to the excavation of the D-wall panels, the ground will relax and the mobilized K value will reduce the horizontal stress during the subsequent excavation. The next few slides just give a high-level construction sequence of the shaft, just for a bit of context. So firstly, the diaphragm wall panels are installed. So elements in red are what's going in, elements in grey are just background for the future. So after the D-wall panels are in, capping beam is cast to tie the tops of the panels together, because there's no reinforcement continuity across the panel joints. The secant piles, which form a temporary wall for the combined sewer overflow installation, are then installed, including a temporary cross wall at a short distance from the shaft. And this is so that the shaft construction and the CSO construction can be decoupled and are not dependent on each other. So there's no propping within the shaft, but there will be temporary propping within the CSO excavation. Next stage is to excavate within the shaft and this first part of the CSO down to the CSO formation level. At this stage, during that excavation, temporary propping would be installed as required in this area. The opening between the CSO and the shaft is then formed in the D-walls. And excavation proceeds down to the formation level of the shaft. Once we reach the formation level, we install a base slab which has a domed shape, and a portion of the cast in situ secondary lining up to a level that sits above the tunnel openings to be made. The shaft is then backfilled up to that level that the secondary lining has been cast to facilitate the TBM to drive through the shaft and form the openings in the diaphragm wall. Once the TBM's passed through, the backfill can be removed and the secondary lining and other internal structures can be completed, and also then the CSO structure can be completed, a base slab, walls, roof slab cast, and then backfill placed on top of that. So that CSO becomes a completely buried structure. So that's the sequence. In terms of the structures that have been modelled for the shaft, they are summarised in this table. So the primary lining, 1 metre thick D-wall, the secant piles of the CSO, temporary wall, and the segmental line tunnels of the Greenwich Connection Tunnel were all modelled as shell elements. I will explain on the following slide how we approximated the secant pile wall as a continuous thickness shell of about 780 mil thickness, and also the reduced thickness of the shell elements applied for the segmental tunnel was due to its segmental nature. But the choice of this thickness, because it's not the primary objective of the model, doesn't have a big impact on the forces in the diaphragm wall, so isn't actually critical. The base slab, which I say is a very large element, so it ranges from 1.5 meters at the edge to 3.4 meters thick, and there's a domed base. And the secondary lining were modeled as volume elements within the shell elements of the primary lining. So whilst the modelling of the secant pile wall as an equivalent shell wasn't actually critical for this model, I've included here an example of how we approximated a wall formed of discrete circular elements to a constant thickness shell. So the secant pile wall in reality was 900 mil diameter piles at 1.2 meter centers with a given concrete strength, unit weight, and stiffness. And to approximate those as a shell, we set up equations equating both the axial stiffness and the bending stiffness for the real world and modeled scenarios, and then solved those simultaneous equations to give an equivalent thickness. So your equivalent thickness drops out as the square root of 3/4 times by the diameter of your pile itself. And this thickness can then be substituted back into the original equations to determine equivalent E value, and also the equivalent unit weight of the wall, which often gets overlooked as it's not actually, doesn't tend to be that critical for retaining walls which are working predominantly laterally rather than vertically. I just noted at the bottom there that if your dominant force in the wall is either bending or axial, it is often acceptable to just calculate equivalent thickness based on either the bending stiffness or the axial stiffness respectively, because the error you're going to get in your results is going to be very small. If the wall is in pure bending, the axial stiffness won't make a big difference. So during construction, the contractor provided us a plan of how the compound was going to be set up and the construction loads that could be expected. So you can see there's a fair few loads there at varying distances from the shaft. So to simplify down the modelling, we considered that a 20 kPa uniform surcharge everywhere around the shaft would be appropriate, rather than having to model all these specific loads which invariably would change on site anyway. In the long term, we're required to consider 3 radial loading scenarios, each with 75 kPa lateral pressure. Scenario A was this 75 kPa applied all around the shaft over its full height. B was 75 kPa applied to just half the shaft, but it could be anywhere. And C, the load applied to a 65-degree zone, but again can be applied anywhere around the shaft. So given that leads us to infinite possible arrangements of this radial load, we came up with a limited number to apply in the modelling, which we considered to produce the worst case forces in the primary lining. And these 5 arrangements are shown here. These are snapshots from the model with the radial load application shown in green. So one scenario with it all the way around, 2 half loading scenarios, and then 2 where it's just applied over specific 65-degree zones. And then in terms of assumptions that went into the model, the primary lining of the shaft itself was modelled as the shell was isotropic and it was perfectly circular. So any forces that would be created by eccentricity of the panels during installation would have to be calculated separately and added to the outputs from the model. The tunnels were effectively modelled as wished in place, and then a lining contraction applied to the tunnel, which equated to a 0.15% volume loss. But you'll see later on, given the way we modelled the connection between the tunnel and the primary lining, the choice of this contraction has actually negligible impact on the results, and subsequently I think we took out the volume loss element and just wished the tunnels in place because it didn't have any impact on the actual answers. And then the final assumption that was made was that the groundwater level within the excavation would be maintained half a metre below the dig level until you cast the base slab, and then the water pressure is allowed to recharge. So those are the key inputs to the model. I'll now pause the presentation to just walk you through the model and various aspects of the software. There's some details there about the model itself in terms of size, number of construction stages that were modelled, the runtime, and also the specification of the machine that it was run on. So it's a fairly large model, taking about 8 hours to run. So hopefully, if I just click there, that's going to show up on your screen. Yep, okay. So I'll start off. This is the GTS NX interface, and this is our full model with it all meshed up. We have what's known as, on the left-hand side here, we have the modeling tree. And if I just make the soil elements around our shaft a bit more transparent, you'll see the shaft and the tunnels sitting within our soil continuum. So also sitting in the model tree are the materials that we assign intrinsic parameters to. So for example, the sand, where we can input all the material properties and select the soil model that we're using. Also put in properties for materials for structural elements, and also interfaces between structures and soils. And these materials are then assigned to properties, which are either so 3D properties for soils and volume elements, 2D properties for shells, 1D properties for beams, and then also for interfaces. And then these properties are assigned to different parts of the mesh. So that's the fundamental modeling process, is that the material is assigned to a property, which is then assigned to the mesh, and the mesh is created from our geometry, which is what I'll just show you now. So I turn all the mesh off. So this is all the geometry that went into building the model. And it starts out, if I turn off all the surfaces that we used for cutting bits, it starts out as essentially a series of overlapping volumes that you create for all the various bits. So we have the different zones for, we have the total soil block, and then different zones for, say, the fine mesh that we want to apply around the shaft. And you create all these overlapping volumes using the geometry modeling tools, or they can be imported from AutoCAD software. But anyone familiar with AutoCAD drawing, a lot of the tools are the same in GTS NX. So we can create all our shapes and geometries. Then we can divide them up with surfaces to chop these geometries into bits. And then once the geometries are all chopped up and you've got all these overlapping areas, there's the auto connect function up here, which then finds all the common faces between those geometry volumes and reduces them down into discrete components, so there's no overlapping geometry. So in this case, we ended up with I think it's about 120 discrete geometry volumes ready for meshing. So the last thing I just want to discuss on geometry before we mesh, we've auto connected all our geometry, so we end up with all these discrete bits of geometry for meshing. You can get more control of your meshing by seeding your geometry. So I'll just show you, say, so we've got the base slab, the lining, and so there we go. That's essentially the geometry we end up with for everything within the primary lining. And then in our model tree, check on this mesh control. You can see areas where we've assigned seeds to the mesh. So around the tunnel, where we want a much finer mesh, we can have great control over where we actually want to place nodes. And doing this before you mesh makes the meshing process a bit quicker, because you can then mesh quite large areas in one go. Tell it what size to mesh it at typically, but then it will also mesh these areas up as you've said if it's finer. So in terms of the meshing, tend to work from the center or the most fine areas of the model outwards, so that you end up with a model that has the granularity of mesh that you're after. We want it to be relatively fine around the shaft, reducing down to a much coarser mesh when we get to the exterior. So you end up on meshing, as I said, we had about 120 geometry volumes. You'll end up with 120 bits of mesh here, but these bits of mesh can then be merged and grouped into rational groups to ease the modeling. So for example, they have made drop downs which just have just the active soil outside the shaft, so these can be turned off and on quickly. So like the excavation can be turned off, other things. So I'll just turn some of this off to simplify it down. And the other thing in terms of generating mesh, so that was, you generated the mesh of all your soil elements. You can generate the mesh for your structural elements by just extracting them from the geometry that was already being created. So the geometry has been used to mesh up the whole continuum. This extract elements function is then useful for just going in to a given geometry element. You know which faces you want to extract the wall from. You extract the mesh set, and then you can be sure that you've got nodal connectivity between your soil and your structure. So once we've got our mesh, turn the geometry off. We've got our mesh, we've extracted all our structures, we've assigned properties to all these mesh sets that sit in this tree. The next step is to define boundary conditions. So you then move from the model tree to the analysis tree, and boundary conditions can be assigned around the perimeter. So for this model, fairly typical, just restraining it laterally on the sides and in 3 translational degrees of freedom on the base. Other boundary conditions that you can see here are for changing properties of mesh sets during the construction. So for say example, the base slab, show so here's our domed base slab. It starts off its life as with just chalk material properties, because that's what it is in the first stage of the model. But later on, we want to change that, reactivate that slab and have its concrete. So we have a boundary condition, which is just the change property, which changes all these elements from a chalk property to a concrete structural property. So there's the D wall, just make that opaque again. So there's our diaphragm wall shell. With openings, which are different mesh sets because we want to deactivate them at certain stages of the model. And then also in the analysis tree, we have, so as boundary conditions, we have our loads, so self-weight, gravity acting downwards, temporary surcharge, so our radial surcharges assigned to the shells. So very simple. There's not a lot of superimposed loads on the model other than these radial loads and temporary surcharges at ground surface. So then once your boundary conditions and your static and your loads are assigned to the model, we have all our mesh, we can create a construction sequence. Which you can see on the left-hand side here, all our stages. I won't go through the sequence again. It basically follows the high-level sequence that I outlined before, but the modeling of the sequence works in GCS-NX that you create the sequence, you create your stages, and then at each stage you can choose. At your first stage, you activate all the mesh that you want for your ground and whatever is there at the start. Boundary conditions such as ground support, self-weight, and that sets your initial condition. You also define water pressures at this stage. Then for subsequent stages, you are just selecting mesh sets that you want to activate, be that installing the walls, changing properties, applying loads, and then also mesh sets that you want to deactivate. So as you see, as we go through the digs, we are removing elements of the mesh. And just so we end up with our sequence, which says about 24 stages. Useful if you have a long sequence and you want to make changes to the sequence, you don't have to recreate the sequence every time. You right-click on stage set, add construction set, and you can copy existing sequences, and those will then appear in the stage set tree, and you can go in and edit that sequence as you wish. So it's very, once you've got your baseline sequence, it's very quick to then create variations on that sequence. And then once the sequence is done, it's just a case of creating an analysis case where we define various bits about the analysis. So if you're adding an analysis case, we're doing a construction stage analysis, and then you have a drop down, and if you had more construction sequences, you'd get all your sequences dropping down here, and you can control various aspects of the analysis, and then also what outputs you see from the analysis. So that's just a quick overview of the model itself and what goes into producing it. I'll then also show you some results and how how we might look at the results. So as well as the model analysis tree, once your model is run, the results tree then populates with all the stage results. And what I would say is, before you start considering any structural results for your shells, it's always a very good idea for that first initial stress stage just to check the stresses in the ground are right from the start, because a lot of the time errors that you will see in models will come from the stress state in the initial condition not being correct. So we can look at vertical effective stress or horizontal effective stresses for the ground, also key pore to pressure to make sure that the model is doing the right thing in terms of how it's defining water at that initial stage. So once we're happy that the stresses in the ground are right, and I'll show a bit more in terms of how we can check that in a bit more detail, we want to look at just our D-wall shell. D-wall. So it disappears because the stage I was showing, it wasn't even activated. I'll go to a stage where it is there, say when we get to the bottom of the shaft, and we can look at shell element forces and say the hoop stress in the shell. So that's the hoop stress when we get down to formation. And you can display these results in a lot of ways. So at the moment, this is just doing the nodal average. You can do it by just the element center result, which gives you a bit more of a granular view. You can do them continuous or fringe, which again gives you a slightly more granular view. You can also turn on contouring, and there's all sorts of ways to display shell results depending on preferences and what you're actually trying to show. You can also show the deformed shape of the shaft alongside the where it started from. And if you want to step through the stage, so this is for the formation stage. There's a scrolling bar here along the bottom that you can drag or wheel through to step through stages. So you can see here as we progress the excavation, how the shaft moves in, and then you'll see at a certain stage we make a hole in the shaft, and as expected, the opening eggs and the sides bend inwards, and the top actually tries to bend a bit outwards. So you get this classic egg shape around the opening. So there's some bending horizontals that are interesting. Vertical bending, let's just go to the stage that is of most interest, which would be once we've created an opening in the shaft. So once you create the opening, you see you get increased bending either side of the shaft. And a tool that I find quite useful for design checks, this is moving on to sort of the design stage rather than modeling, is this ISO value surface, where we can define a range of values to show. So if you know the capacity of your wall, you can pop in a capacity there and show all the areas of the model where you're exceeding that capacity. So very useful for quickly checking and defining areas of your structure where you might have issues or need for additional reinforcement. So the results come out for individual stages, but again for design, we probably want to envelope those. So there's the combination function up in the top left, where you can select an analysis, you can select whichever stages you're interested, add them in there, and then create envelopes, either maximum, minimum, or absolute envelopes of your results, and that'll envelope everything. It's not just for the given result you're on, it'll do all your results. And so just like Blue Peter, here's one I made earlier. So there's the maximum envelope. And again, it just gives all your results. So now I look at the bending. That's showing me the maximum values throughout the whole sequence. And again, you can assign an ISO. You can do an ISO surface on that to check things. The other useful function in terms of the results is the cutting diagram. So we can, if we want to look at create curves of specific results, we can either cut a line or a plane on our structure. This, give it a direction, define how many points we want to look at, and then you apply and it'll create a diagram. A bit tricky to see there, but then we have a tool where you can clip. I'll come on to the clipping tool in a second. But essentially, you can see here, there's a lot of these on-curve diagrams already created. Let's delete that one. And they stay embedded in the model forever. So even if you rerun the model and the results change, the on-curve diagrams remain in the results file. So they're always then, once they're created, they're always accessible to check things. So if I'm looking at the primary panel, vertical in the X direction, yes, we've already got an on-curve diagram there. So I say the D-wall itself is masking that, but there is this clipping plane function here on the left-hand end of the toolbar, where we can create a plane and actually cut our results. So then you can cut through the wall and show the bending moments at that location where you're interested in. This is just the envelope, obviously, so I went back so the results don't look terribly sensible. Let's just go back to a stage where they might do. So there we go. One other thing, and I realise time's pushing on, that I wanted to just show is in terms of, we talked a bit about checking stresses in the ground, and one thing that I find useful to do is, well, one thing that you can do in the results is you can do a calculation of results. So if I want to check the mobilized earth pressure in my analysis, so the K star I have when I get to the formation level, I can look at a given stage. So at formation, I can look at solid stresses, horizontal effective stress of that, vertical effective stress, add that, and I can do a calculation that is horizontal over vertical. I'll call it mobilized K. Let's give it a name there. And then if you create that, it creates another result output, which is a sort of bespoke output that I've created, which is my mobilized K value, and it's the ratio between your horizontal and vertical effective stresses. I can then turn on my active soil if it wants to respond. Okay. Okay. So there's my active soil, and I've the clipping plane is still activated. Double click on my result that I've just created, and because of there's some very small elements that will give you some funny numbers, you can adjust your legend to show just a sensible range of numbers. So let's just go up to 3. Apply. Okay. And so then this is, and that on curve, let's just, and then I already have another on curve diagram that is just sat just within the active soil, so just outside the wall. And so then this is showing effectively my K mobilized down the wall. So you can see that in the Thanet sand, which had a K0 started out at 1, we're still very close to that, 0.95 maximum. So not a lot of relaxation there, but down towards the formation level where we're getting a lot of movement, we're getting down to about 0.3, which is close to close to sort of the Ka limit for the chalk. So this is again a useful tool for checking stresses and behaviour of the ground, which is fundamentally what we want to be doing, to ensuring that the ground behaviour is correct, so therefore we can have confidence in the structural behaviour. So I think that's all I want to say on the actual model. I'll go back to the presentation now. And just talk about one of the key aspects of the modelling which we had to resolve, which was that the structural connections. And this is one that occurs frequently when modelling underground infrastructure, that you have adjacent structures that are in contact, but they don't actually transfer significant forces. And that's a problem in FE modelling where we can't have gaps. So where the tunnels pass through the diaphragm wall and there's no actual connection between the tunnel and the primary lining, this was resolved by omitting the first row of elements of the tunnel, so there was no connection between the two structural shells. And to ensure we maintain stability of the ground across that artificial gap, we updated the properties of the in situ chalk local to the opening, such that they were very, very strong, but still with 0 tensile strength, and relatively soft, so that the tunnel could deform as it wanted to upon contraction without transferring significant forces into the D-wall. And we also did this for the connection between the secant pile wall and the shaft itself. So again, we have these elements which are high strength but low stiffness, so that this wall can move relatively freely compared to the shaft. So I've already shown you a few of the results, but I'm just going to discuss them in a bit more detail to finish off, particularly how they're affected by the secondary lining of the shaft. Because the interface between the diaphragm wall and the cast in situ secondary lining is quite difficult to assess in this case, because there's no actual structural connection between the two that would allow you to justify and be happy with a purely rigid connection. So there is an interface, there is some resistance between the two, but it's difficult to know what it is. So we ran a number of models to bound the loads on the primary lining, which was our main objective. So we did a model without the secondary lining at all, which was expected to give us an upper bound on the forces in the D-wall, and then also a model with the secondary lining included but rigidly connected to the primary lining, and that's model 2, and that should give us a lower bound on the D-wall forces because the primary lining will carry some of the load. And then we also set up a model that still just had a single shell for the shaft, so it's just the primary lining, but at the relevant stage we updated the properties of that shell to give us the equivalent properties of the combined secondary and primary lining. And this was just to see if the forces for the individual elements themselves could be reliably inferred from the outputs just based on a single shell, because a single shell is quicker to model, quicker to run, and if we can get numbers out for both elements just from a single shell, that's a improvement in the efficiency of the modeling process. So here's just some of you've seen these typical outputs already from the model. The critical bit being the forces around the opening as they're created. This is where you'll get tension forming vertically either side of the opening. So our baseline model without any secondary lining, it was important that we validated and sense checked the outputs before we used it for design. We did this in two ways. Firstly, by checking the stresses around the opening against a closed form solution for a hole in a stress plate, and those numbers came up looking sensible. And we also compared the results with those for a similar size shaft on the project that had been modelled using FLAC 3D, which can be seen here in the table to be very similar. Once an allowance was made for the difference in material properties outside the shaft. And both of these gave us confidence that the model was behaving as we expected, and the results could be confidently used for the design checks. This table shows the forces around the tunnel opening for both Model 1 and Model 2, where we included the secondary lining. Remember that Model 1 is a single shell with the combined properties of the primary and secondary lining, and Model 2 has them separated out, one as a shell, one as a volume. And you can see that in both models, the Hoopt force at the crown increases and axial forces beside the opening increase as expected. The bending moments also change as you'd anticipate, but the absolute values here aren't as important as how the change in load is shared between the two linings, which I've summarized on the next slide. So this shows how the forces actually change between as the opening is formed. So in Model 2, the Hoopt forces are shared between the primary and secondary lining in a ratio very similar to their axial stiffnesses. So the D-wall's 1 meter and the secondary lining is 650 millimeters. Whereas the vertical bending is shared similar to the ratio of bending stiffnesses, which is what I would expect. The horizontal bending is also shared in the same proportion as vertical bending, but this is only due to the isotropic shell assumption made in the modelling. In reality, the joints in the diaphragm wall can't carry significant horizontal bending, therefore all the horizontal bending induced by the tunnel opening will need to be carried by the secondary lining. So that is all this additional bending goes into that secondary lining. The main anomaly that we identified by Model 2 was that the increase in tension next to the opening was disproportionately carried by the secondary lining. And I think this is most likely due to the geometric effects of the secondary lining being modelled at an offset to the primary lining. So as the opening eggs and the sides tend to bend inwards, which creates additional tension on the inside face of the lining. If you imagine the two linings rigidly connected and bending like a beam, the primary lining will sort of act as the compression zone of that beam, and the secondary lining carrying the equivalent tension. So I think that's why, as we open up in that model, you see the primary lining take a touch more compression and the secondary lining take a lot of tension. How realistic that is, I'm not certain. It's probably down to the rigid connection between the two. So, because in reality, as they bend, there'll be some slip between the two linings. But what I could say is that using that number would be a conservative value with which to design the secondary lining. So from those models, we were able to conclude that the baseline model without the secondary lining provided an upper bound on the D-walls forces, and those were used to undertake the independent checking. And the test models that we ran with the secondary lining included indicated that if you can accept a reduction in accuracy, so say you're just looking at the preliminary sizing of elements, modeling these two linings could be approximated by a single equivalent shell, and the results divided pro rata based on the relative stiffnesses, as long as you were aware of how you expected the forces to actually distribute. So those are the main conclusions that we were able to make. And so now I'll just finish with a very few photos just of the actual construction. So there's a bird's eye view of the site itself during construction. Excavation's already started at that stage. There's another compound photo, and then a couple of photos of the shaft itself. So it's a view from the bottom looking up, and then also starting to fix the base slab reinforcement. And finally, that's just an artistic impression of what the green will look like once the shaft is fully completed and everything's put back to the way it is. So thank you everyone for listening. I've just gone over an hour, so apologies if people were expecting it to be a bit shorter. I'll just have a look and see what we've got in terms of questions. I'll just take a minute to have a look through these questions and pick out a few ones that I think will be of interest to the majority. So I can see one here that's asking about extraction of forces and moments from the secondary lining, if this is modeled with volume elements rather than a shell. And that was done using a gauging shell element, similarly for the base slab, which again is just an extracted shell that is essentially infinitely flexible compared to the volume it's attached to, that results can be extracted from in the typical ways you would for the shell. Did we consider orthotropic stiffness case of the D wall to represent the effect of joints between panels? We have in the past applied an orthotropic shell for D walls. I think in GTS-NX you can push the orthotropic ratio for shells to about 5 to 10 times the relative stiffnesses. Beyond that, I've found that the results start to become a bit strange. To really model it more accurately, you can model the panels as volume elements themselves with gauging shells and extract those values, which we've done on other projects where we've needed to have a higher level of accuracy. But for this case, we were just, as I say, undertaking an independent checking role. So it's really a case of satisfying ourselves that what is shown on the drawings will work in practice. We used a reduced K0 for modelling the impact of the excavation. Did you increase the K0 for the final stage or to model the long-term condition where the horizontal forces may, and I can't see the rest of the question, but we didn't for the long term because, well, we're applying 75 kPa all around, which is likely, which will account for some of that. We did do some sensitivity studies in terms of using higher in situ stresses just to make sure we were bounding the problem correctly. Just confirm, yes, the groundwater is hydrostatic, but you can model subhydrostatic conditions in GTS-NX. So there's a few questions in terms of the domed base slab. The base slab is domed just because the water pressures at the base will be very significant, and it's not actually connected to the D wall. So it's domed so that you get the upward force then will arch and apply a lateral pressure onto the wall. It's really to redistribute the forces coming through the base slab so they're more lateral into the wall rather than vertical. Few questions about movements during construction. I've not seen any movement data yet. That would be interesting. One more. Question about London soil conditions and about modelling of the materials as drained. Why didn't we look at undrained in the short-term case? Well, the thanate sand and the gravels will always behave in a drained nature, and the chalk to a certain extent as well. We could have looked at an undrained analysis in the short term, but it wouldn't have governed. So I'll conscious that it's now been going over an hour and people have other things to do. So I will look through these questions in more detail and provide some more sometime in the near future. But other than that, I'll say thank you very much to everyone for attending, and I hope you enjoy the rest of your day and week. Thank you all. Bye-bye.